In computer graphics, alpha compositing is the process of combining an image with a background to create the appearance of partial or full transparency. It is often useful to render image elements in separate passes, and then combine the resulting multiple 2D images into a single, final image called the composite. For example, compositing is used extensively when combining computer-rendered image elements with live footage. In order to combine these image elements correctly, it is necessary to keep an associated mat for each element. This mat contains the coverage information the shape of the geometry being drawn making it possible to distinguish between parts of the image where the geometry was actually drawn and other parts of the image that are empty. Description: to store mat information, the concept of an alpha channel was introduced by Al V. Ray Smith in the late 1970s, and fully developed in a 1984 paper by Thomas Porter and Tom Duff. In a 2D image element, which stores a color for each pixel, additional data is stored in the alpha channel with a value between 0 and 1. A value of 0 means that the pixel does not have any coverage information and is transparent. That is, there was no color contribution from any geometry because the geometry did not overlap this pixel. A value of 1 means that the pixel is opaque because the geometry completely overlapped the pixel. If an alpha channel is used in an image, it is common to also multiply the color by the alpha value, to save on additional multiplications during compositing. This is usually referred to as premultiplied alpha. Assuming that the pixel color is expressed using straight RGBA tuples, a pixel value of implies a pixel that is 50% of the maximum green intensity and 50% opacity. If the color were fully green, its RGBA would be. However, if this pixel uses premultiplied alpha, all of the RGB values are multiplied by 0.5 and then the alpha is appended to the end to yield. In this case, the 0.5 value for the G channel actually indicates 100% green intensity. For this reason, knowing whether a file uses premultiplied or straight alpha is essential to correctly process or composite it. Premultiplied alpha has some practical advantages over normal alpha blending because premultiplied alpha blending is associative, and interpolation and filtering give correct results. Ordinary interpolation without premultiplied alpha leads to RGB information leaking out of fully transparent regions, even though this RGB information is ideally invisible. When interpolating images with abrupt borders between transparent and opaque regions, this can result in borders of colors that were not visible in the original image. In addition, premultiplied alpha allows regions of regular alpha blending and regions with additive blending mode to be encoded within the same image. Premultiplication causes a loss of precision in the RGB values, so that a noticeable loss of quality can result if the color information is later brightened or if the alpha channel is removed. This loss of precision also makes premultiplied images easier to compress, as they do not record the color variations hidden inside transparent regions. With the existence of an alpha channel, it is possible to express compositing image operations using a compositing algebra. For example, given two image elements A and B, the most common compositing operation is to combine the images such that A appears in the foreground and B appears in the background. This can be expressed as A over B. In addition to over, Porter and Duff defined the compositing operators in, held out by, atop, and XOR from a consideration of choices in blending the colors of two pixels when their coverage is, conceptually, overlaid orthogonally. The over operator is, in effect, the normal painting operation. The in operator is the alpha compositing equivalent of clipping. As an example, the over operator can be accomplished by applying the following formula to each pixel value. Where is the result of the operation, is the color of the pixel in element A, is the color of the pixel in element B, and under the alpha of the pixels in elements A and B respectively. If it is assumed that all color values are premultiplied by their alpha values, we can rewrite the equation for output color as and resulting alpha channel value is examples of red overlaid with green with both colors fully opaque. Analytical derivation of the over operator. Porter and Duff gave a geometric interpretation of the alpha compositing formula by studying orthogonal coverages. Another derivation of the formula, based on a physical reflectance transmittance model, can be found in a 1981 paper by Bruce A. Wallace. A third approach is found by starting out with two very simple assumptions. For simplicity, we shall here use the shorthand notation for representing the over operator. The first assumption is that in the case where the background is opaque, the over operator represents the convex combination of and. The second assumption is that the operator must respect the associative rule. Now, let us assume that and have variable transparencies, whereas is opaque. We're interested in finding. We know from the associative rule that the following must be true. We know that is opaque and thus follows that is opaque, so in the above equation, each operator can be written as a convex combination. Hence we see that this represents an equation of the form by setting and we get, which means that we have analytically derived a formula for the output alpha and the output color of. An even more compact representation is given by noticing that. It is also interesting to note that the operator fulfills all the requirements of a non-commutative monoid, where the identity element is chosen such that alpha blending is the process of combining a translucent foreground color with a background color, thereby producing a new blended color. The degree of the foreground color's translucency may range from completely transparent to completely opaque. If the foreground color is completely transparent, the blended color will be the background color. Conversely, if it is completely opaque, the blended color will be the foreground color. Of course, the translucency can range between these extremes, in which case the blended color is computed as a weighted average of the foreground and background colors. Alpha blending is a convex combination of two colors allowing for transparency effects in computer graphics. The value of alpha in the color code ranges from 0.0 to 1.0, where 0.0 represents a fully transparent color, and 1.0 represents a fully opaque color. This alpha value also corresponds to the ratio of SRC over DST in Porter and Duff equations. The value of the resulting color is given by: if the destination background is opaque, then, and if you enter it to the upper equation. The alpha component may be used to blend to red, green and blue components equally, as in 32-bit RGBA, or, alternatively, there may be three alpha values specified corresponding to each of the primary colors for spectral color filtering. If premultiplied alpha is used, the above equations are simplified to. Other transparency methods, although used for similar purposes, transparent colors and image masks do not permit the smooth blending of the superimposed image pixels with those of the background. A similar effect can be achieved with a 1-bit alpha channel, as found in the 16-bit RGBA HIG color mode of the TrueVision TGA image file format and related TARGA and AT-Vista NU-Vista display adapters HIG color graphic mode. This mode devotes 5 bits for every primary RGB color plus a remaining bit as the alpha channel. See also, RGBA color space, digital compositing, transparency, transparent color in palettes, image masks, portable network graphics, TrueVision TGA, Magic Pink, texture splatting, alpha to coverage. References. External links, Compositing Digital Images, Thomas Porter and Tom Duff, Image Compositing Fundamentals, Understand Compositing and Color Extensions in SVG 1.2 and 30 minutes. Alpha matting and premultiplication.